All right, time to rise and shine, statisticians. Chapter 7 is the chapter that waits for no man slash woman slash however you choose to identify. So here we're going to talk about an introduction to ANOVA. ANOVA is, in this case, a little different than the ANOVA table. In this context, it's referring to an analysis of variance. So how do we define a one-way ANOVA? So we're going to start. There's lots of different ANOVAs. You're actually going to do a lot of ANOVAs and go really deep into kind of this type of model in Stat 513. So kind of this lecture in some ways is kind of bridging the gap between 512 and 513. So we're going to end with this, and this will be actually where you end up starting when you take 513 next semester. So the simplest type of ANOVA is referred to as a one-way ANOVA. A one-way ANOVA has a continuous response variable y, a single nominal independent variable, so a categorical independent variable with no inherent ordering, and multiple observations within each category of the independent variable. So more than one observation for every category. A little bit of vocabulary. When we're talking about ANOVAs, we refer to the nominal variable under consideration as the factor. And we refer to the categories of the factor as its levels. So the ANOVA has some assumptions. They're actually essentially the same four assumptions that we had in when we started talking about regression. The first is that we have random samples. Random samples have been selected from each of the K groups or categories. Right? So maybe like kind of harkening back to our discussion of dummy variables and interaction. I think we did an example where we looked at like university affiliation. So the idea is we took a random sample from Westchester, a random sample from Temple, a random sample from Penn State. This is essentially the what? It's essentially the independence assumption, isn't it? So kind of since we're taking a random sample, that's going to imply independence amongst our observations. The dependent variable within each category follows a normal distribution. And the variance of the dependent variable is the same in each population, in each category. So sort of the variability in GPA for Westchester students is the same as the variability in GPA for Temple students is the same as the variability in GPA for Penn State students. So that's our homogeneity assumption. So the ANOVA assumption is very, very similar to the regression assumptions that we've already mastered. Now, what if these assumptions are violated? Well, not that big a deal. The ANOVA will work reasonably well as long as none of the assumptions are grossly violated. That is, they're not severely violated. This means that the ANOVA is what's called a robust procedure. Robust basically means that minor violations of the assumptions are not that big a deal. It still works well when there's only minor violations of these key assumptions. Just like with regression, the most important assumption, the one that's most critical, the one that needs to be remedied if in fact it's violated, is the independence assumption. And just like with regression, if we have violations of normality and homogeneity of variance, we want to fix them. They can often be fixed with some type of transformation of the y variable. All right, so let's take a look at this in the context of an example. I took this example from our textbook. There were 5 treatments assigned to 30 patients. And these 30 patients had these things called fever blisters. So 5 treatments, 30 patients. So 6 patients got each of the 5 treatments. And for every one of these patients, we recorded the number of days that it took until their fever blisters completely healed. And in terms of treatments, treatment number 1 was the placebo treatment. So treatment number 1 was just some sort of like kind of fake ointment. I don't know, some type of translucent or transparent peanut butter that was being rubbed on the fever blisters. Whereas 2, 3, 4, and 5 were presumably had some hopeful medicinal properties. All right, so for those of you that want to play along at home, here's what the actual data set looks like. So you can see we have 30 patients. First 6 patients were assigned treatment 1, the placebo. Next 6 patients were assigned treatment 2, and so on. And then for every one of these patients, we recorded on average how long, exactly. For each patient, we recorded exactly how long it took until their fever blisters went away. So in terms of our vocabulary, the factor is the treatment, right? The nominal variable, in this case, the variable is treatment, and the levels of treatment are kind of these just generic levels, right? Placebo, treatment 2, treatment 3, treatment 4, treatment 5. Now, what are some questions that we might ask? Well, one pretty straightforward question is, are all of the treatment means for each of the 5 groups the same? That is, do they all behave the same, or are some, right, the negation of that would be some are better than others? And if in fact they're not the same, if some are better than others, right, which are in fact the better ones? Which treatments are they all the same? That is, does it matter? And if it does, right, how do we dig deeper? How do we dig deeper to find out which are the effective treatments? So just like with regression, we start with an overall F-test. The overall F-test is a little different than the regression one. The regression one, remember, was beta 1 equals beta 2 equals beta 3 equals beta k, all equal to 0. Here, our null hypothesis is that the mean for population 1 is the same as the mean from population 2, which is the same as the mean from population k. They're not necessarily 0. In fact, probably they're not 0. But all we're stating with our null hypothesis is that they're the same. And of course, the alternative hypothesis is the negation of that there's at least 2 means that are different than one another, maybe more. Now, to perform this test, we build the usual ANOVA table that decomposes SSY, the overall inherent variability in Y, the variability in healing time for these fever blisters, into SSR, the amount of variability explained by the treatments, and the remaining leftover variability, SSE. We then define MSR as SSR divided by K minus 1, the number of categories minus 1, and MSE as SSE divided by N minus K. We can show mathematically that the ratio of MSR over MSE follows an F distribution with K minus 1 degrees of freedom in the numerator, N minus K degrees of freedom in the denominator. Now note, in an ANOVA, we often use SST and MST instead of SSR, MSR. So SST, it usually stands for the sum of squares treatment or the mean squares treatment, because in an ANOVA context, what we're often comparing is different treatments. So in some books, in some literature, some colleagues or bosses down the road, they might use SST instead of SSR, but it's meaning and referring to the same thing. So very, very similar to regression yet again, right? We're seeing an awful lot of parallels between one-way ANOVA and what we've already learned in terms of regression modeling. So ways of conceptualizing this overall test. This overall test can be conceptualized in a few different ways. The first is that it's a generalization of the two sample t-test. So one of the last things that you probably did in your general education statistics class that was a prerequisite for this course, one of the last things that you probably did was you did these sort of two sample t-tests where you're comparing the means of two different groups. The ANOVA generalizes this. Instead of comparing the mean of two different groups, we're comparing the mean of K different groups. We can also conceptualize this, just like we did for regression modeling, as looking at the ratio of two estimates of the variance. And then finally, we can look at it as comparing the variability between groups relative to the variability within groups. Okay? That is, if our null hypothesis is violated, if some treatments are better than others, then we expect to see a large variability between the groups. If they're all identical, if none are in fact better than the others, we expect to see relatively little, a small amount of variability between groups. Okay. So in terms of the ratio of those two estimates of variance, just like in regression, we can show that the MSE estimates that common homogeneous variance, sigma squared. And similarly, it can be shown that MST estimates sigma squared plus that extra quantity. That extra quantity is essentially 0 whenever all the means are the same. That is, under the null hypothesis. Under the null hypothesis, MST, the expected value of MST, is the same as the expected value of MSE. So in that situation, we expect an F statistic close to 1. Now, if the null hypothesis is not true, right, that extra quantity has to be positive, so that numerator now becomes larger than the denominator, and the F statistic becomes larger and larger and larger. So we can see why large F statistics correspond to a stronger amount of evidence that we should reject the null hypothesis. All right. So in terms of notation, right, that summation is 1 through K, so we're summing up over all the K groups. N sub I is the number of subjects in the ith group. So for our fever blister example, N sub I is 6. Mu sub I is the mean of group I, right? So the mean time for the blisters to heal for group I. And that mu bar is like the overall mean, the mean of the means. In terms of comparing the variability between groups relative to variabilities within groups, it could be shown mathematically that SST could be written as N sub I, yi hat, so the sample mean for group I minus y bar, the overall sample mean. So what is that? That is essentially the variability between the groups. That's our SST. And then we can see the SSE is the variability within the groups, the actual variability of the actual observations, Yij, amongst their group mean, Yi bar. So SSY decomposes into this SST plus SSE, where SST can be conceptualized as the variability between groups, and SSE can be thought of as the variability within groups. Yeah. SST is often referred to as between group variability. SSE is often referred to as within group variability. All right, so cool trick that we're about to learn, actually a bit of a game changer, is that we can feed this categorical variable into SAS, even if, so in this case, I think our treatment is coded numerically. If our treatment had been coded like as a word, so like treatment 1 was just written out as placebo, and then treatments 2 through 5 were actually like the name of the treatment, we could still feed it into SAS if we use procglm through the class statement. The class statement is a game changer. It saves us so much time. So we put the categorical variable, that nominal variable, we put it in the class statement. And then we just write model y equals x, where x is our categorical variable. And then here is our output, right? So we have our ANOVA table. Notice the degrees of freedom are 4. That's k minus 1, right? We had 5 categories, so k minus 1, 5 minus 1, 4 degrees of freedom. N minus k, so our n in this case was 30. 30 minus 5 degrees of freedom in the error. So our ANOVA table all fills in, gives us an F statistic, gives us a p-value. Our p-value is 0.0136, 0.0136. So what is that saying? It's saying that, right, at least 2 treatments, maybe more, at least 2 treatments have a difference in terms of how long at average it took for them to heal up the blisters. So the natural follow-up question now becomes, which are the 2 treatments that are different? And are there more than 2 that are different? Right? So the significance of our overall test prompts us to dig deeper. The question that we have to now answer is how. Yeah, so at the 0.05 significance level, at least 2, maybe more, of the treatments have a different mean healing time. Now, a question for you, because I'm actually starting to get a little suspicious here. It seems an awfully lot like regression, right? And what do they say? They say if it looks like a duck, if it quacks like a duck, are you thinking what I'm thinking? Maybe it is in fact a duck. So before we talk about how to dig deeper, my question to you is, could we have done this analysis using techniques that we've already learned? And the answer should be, yes, we can. How? How have we already learned to tackle a problem like this? We've learned how to tackle a problem like this with dummy variables, right? A few weeks back, right, we looked at an example. The example compared the GPA for 3 different universities. That's exactly what we're doing with a one-way ANOVA, isn't it? That's just a one-way ANOVA where k equals 3. And we saw that we could do that by creating dummy variables. How many dummy variables did we make? We made k minus 1 dummy variables. So 3 universities meant 2 dummy variables. Yeah, there it is. So here we have 5 treatments. That means we need 4 dummy variables. It makes sense to make the placebo our reference category, and then we just look at how well each treatment works relative to the placebo. Yeah, pretty easy, right? It is pretty profound though, right? Because this is maybe giving us an appreciation of how powerful that class statement is. Because we did know how to do this, but it was pretty cumbersome, wasn't it? That is, we had to create these dummy variables and then plug these 4 variables into our model. It turns out the class statement basically tells SAS to do all this extra work for us. Pretty nice, right? And now all the parallels we saw between regression modeling and ANOVA all make sense because what? Because an ANOVA is just a special case of this broader multivariate regression modeling. That's the whole idea behind GLM. GLM, general linear model. A general linear model is a sort of general way of looking at things that looks at regression modeling and ANOVA modeling, which a lot of non-statisticians look at as 2 different things. We, as practicing statisticians, understand that they're really the same thing. And ANOVA is just a regression model where we created a bunch of dummy variables. And we can ask SAS to do that through the class statement. Pretty cool, right? So here's our output. Notice we actually do get a little bit of extra information. So, right, the ANOVA table should be exactly the same. That F statistic 3.9 is exactly the same as we got from our previous output. The p-value 0.0136, exactly the same. What is a little different, right, that we have a little bit of extra information here in our dummy variable approach because why? We can actually write out this this prediction equation, can't we? And using this prediction equation, we could look at like the estimates, the predicted values, which are essentially the means of these different groups. Right? Write out that prediction equation. y hat equals, right, 7.5 minus 2.5 times x1 minus 3.16 times x2, and so on. That's our global equation, and by plugging in different values for our treatment, we could come up with the means for these different treatments. Now remember, this is the amount of time it takes to heal, so smaller numbers are better. Yeah. So our conclusion are exact same p-value, that 0.0136. So again, this is verifying that this is in fact the same thing, but we do have that additional information I pointed out. We have our model equation. Right, the y-intercept is the average time of healing for the placebo. So the placebo takes 7.5 days on average for a fever blister to heal. All the other treatments took less than that. The p-value for each of those, the x1, the x2, the x3, the x4, the p-value associated with those x's was saying whether or not that treatment was significantly different than placebo. In this example, all of those had p-values less than 0.05, with the exception of treatment 5, and hence are significantly different than the placebo. And then here's that actual prediction equation, right? So you should be able to verify these numbers. They're all coming off that prediction equation. If you do not see where these numbers are coming from, that's a problem, and you should reach out to me. So the estimated mean time for treatment for the placebo, 7.5 days. For treatment 2, that's 5 days. For treatment 3, which appears to be our best treatment, 4.33 days. The worst actual treatment, right? The worst non-placebo treatment is treatment 5, 6.17 days, which we saw was not significantly different than treatment 1. So it sort of didn't overcome the placebo effect. Yeah, so there's our implications. Pretty cool, right? ANOVA is actually just a special case of multiple linear regression. PROC-GLM is still using dummy variables in its analysis. It just creates them and uses them behind the scenes. Streamlines the process. So we have now concluded, right, p-value 0.0136, that at least 2 of the means are different. We now need to probe deeper to find out which means are significantly different from one another. Right? None of that information was provided by PROC-GLM. Some of that information was provided with PROC-REG. Right? PROC-REG compared treatment 1, the placebo, to 2 and 3 and 4 and 5. But even with PROC-REG, we don't have information comparing, for example, treatment 5 to treatment 3. So how could we do something like that? How could we go about comparing any 2 means? How can we dig deeper to see exactly which of the means are different? Well, first off, let's think about how many sort of pairwise comparisons there actually are. It turns out there's 10 of them. And in this case, it's not too hard to kind of just enumerate them all. We could compare group 1 and 2, group 1 and 3, group 1 and 4, group 1 and 5, groups 2 and 3, 2 and 4, 2 and 5, 3 and 4, 3 and 5, and groups 4 and 5, right? Now you may or may not have taken Stat 505. It's not a prerequisite, although most students will have taken it. if you have taken Stat 505, the answer to this question is 5 choose 2. Right? That's a counting tool. We learned how to count in Stat 505. It's part of our probability calculations. And go ahead and verify that 5 choose 2 is 10. We have 5 groups. How many different ways can you put 5 groups into a group or 5 elements, 5 units into groups of size 2? Could be done in 10 ways. If you haven't taken it 505, no big deal. Hopefully you can just see that it's 10 from me just listing them all out. More generally, if I have k of these groups, k treatments, the total number of pairwise comparisons now becomes k choose 2. So we have these 10 possible tests. We have these 10 possible pairs that need to be compared with one another. How? How do we go about doing it? Well, one way we can go about doing it is through the contrast statement. The contrast statement works like this. So you write out contrast. You can put a title to your contrast. That's why I did it in purple. It's not required, but particularly if you're doing more than one contrast, it's useful. And then you put a 1 and a -1 for the 2 groups that you want to compare, and zeros for everything else. You're going to go into, like I said, this is kind of like an introductory lecture for 513 in a lot of ways. And in 513, you're going to go into a lot more detail, a lot more depth with the contrast statement. So I'm not going to get into too deeply like why this works and what's going on with the 1 and the -1. For now, hopefully you could just kind of take my word for it. You have these 5 different numbers. 1, -1, 0, 0, 0. The 5 numbers correspond to our 5 treatments. If you want to compare any 2 of them, you put a 1, a -1, and everything else 0. So if we wanted to compare treatments 2 and 4, why don't you write down what that would look like? Why don't you take a second, pause the slide if you have to, and write down what the contrast statement would look like if you wanted to compare groups 2 and 4. And again, you have the data. So if you really want to learn this, do this in SAS. Don't just stare at my PowerPoints. Get involved. The contrast statement to compare groups 2 and 4 would look like 0, 1, 0, -1, 0. Okay? So we can use the contrast to do any one of our 10 comparisons. Yeah, so here we are, comparing 1 and 2, 0.009, which incidentally, if you go back to our proc-reg output with the dummy variables, you'll see matches that proc-reg output. As well it should, it's doing the same thing. So it's easy enough, a little cumbersome, but I guarantee you, if you just sat down and did it, you could type out all those contrasts in probably less than 2 minutes. So it is easy enough to use the contrast statement to do all of our 10 possible pairwise comparisons. But before we do that, I want us to consider a pretty important statistical topic. And again, it's a topic that's much more general than what we're talking about in the context of a one-way ANOVA. And that is type 1 error rate. We talked a little bit about this when I very first introduced the chunkwise test. And I said that we would talk about it in greater detail down the road. Well, here we are down the road. We can think of the overall type 1 error rate as the following. The probability, that's what that capital P stands for, the probability of rejecting at least 1 out of M tests given that all null hypotheses are true. So we're used to this idea of a type 1 error. Usually when we talk about type 1 error, we're talking about just doing a single test. So we say, okay, if I use an alpha of 0.05, if I use a significance level of 0.05, then my type 1 error, my probability of rejecting the null hypothesis when I shouldn't, when it's true, is 5%. Now we're talking about a more complex situation. What if instead of 1 test, we're doing 10 tests? If we compare the p-value for every one of these 10 tests of 0.05, we have a 5% chance of falsely rejecting the null hypothesis for any one of these tests. But what about if we look at all of the tests together? That is, what's the probability of making at least one mistake? It should be intuitive that if we use a 5% for every one of those 10 tests, the probability of us making a mistake on one or more of those will be more than 5%. However, what we would like as statisticians is what we want is not the significance level of a single test to be 5%, but the overall type 1 error rate to be 5%. Okay? What we would like to do anytime that we know we're going to be doing multiple tests, this is what this is called. It's called multiple testing or multiple comparisons. Here we got 10 different comparisons. We're doing multiple comparisons. And what we're learning is something called a multiple comparison adjustment. We're going to adjust the process that we use in such a way to make the overall type 1 error rate 5%. And let's see how we do that. Well, we'll actually look at 2 ways to do it, and there's more than 2. I'm just going to focus on these 2, and I'll tell you why I picked these 2 in just a minute. The first possible solution we're going to discuss is something called a Bonferroni adjustment, and the second method that we're going to discuss is something called a Tukey-Kramer method or a Tukey-Kramer adjustment. So the Bonferroni adjustment is based on the idea that we can show, it can be shown mathematically, that if you're doing M tests, the overall type 1 error rate is at most M times alpha, where alpha is what is the significance level used for the individual test, right? So the idea is if you were doing each individual test and comparing the p-value to 0.05 and you're doing 10 tests, the overall type 1 error could be as high as 50%. And so with this in mind, the easiest fix, and the problem with this is it usually ends up being sort of too much of an adjustment. It kind of over adjusts because it's kind of accommodating a worst case scenario. It's saying, right, all we're saying is that the overall type 1 error rate could be as high as 50. Probably it's less than 50. But what we're doing is we're adjusting for the worst case scenario. And so what we basically do is instead of using 0.05, we use 0.05 divided by m. So 0.05 in our case divided by 10. 0.05 divided by 10 is 0.005. Becomes a lot harder to reject now, doesn't it? Instead of something less than 0.05, right? Now it has to be less than 0.005. Right? Because again, if we do 10 tests all at the 0.05 level, then our overall type 1 error is now at most 0.005 times 10. It's now at most 0.05, right? Which is exactly what we want it to be. Do we see that? Yeah, pretty cool, right? One of the nice things about Bonferroni, the Bonferroni adjustment, actually I think I have it on the next slide. Let's take a look. Yeah, one of the nice things about the Bonferroni adjustment is that it's very general. It is in no way restricted to doing these multiple comparisons, these multiple pairwise comparisons. Anytime in statistics, it's pretty powerful. You don't get to say this very often. Anytime in any statistical context, if you're doing more than one hypothesis test and you want to adjust for the fact that you're doing multiple tests, you could just look at the total number of tests and do 0.05 divided by that, and that becomes your new thing that you compare the p-value to. In fact, here's a pro tip. If you ever find yourself in a situation where you have to use Bonferroni, there's actually a process called Bonferroni-Holmes that also is universally applicable and also could be shown to be universally better than Bonferroni. So Bonferroni, the problem is that it's often overkill. And the Bonferroni-Holmes process, Bonferroni H-O-L-M, Bonferroni-Holmes, is that one's a little less of an overkill, but still universally applicable. It's not in our textbook, so I didn't get into details, but if you Google it, you can find its Wikipedia article, and it's not particularly hard to implement. Okay? This is important. It is a big deal, although I will say a lot of researchers, a lot of practitioners, and even some statisticians kind of wave away this idea of multiple comparisons. Because why? Because we often want significance, right? We often want things to be significant. That means that our research is good, and so right now we get our PhD, or now we get our paper published, or now, right, our drug has just been proven to work well, so we can just make $1 billion. We often as human beings want significance, and so, right, we game the system. Maybe consciously, maybe unconsciously, a lot of times without really understanding or knowing that we're doing it. Like, you think about sometimes, like, I don't know, like maybe you're watching like Oprah. Yeah, I don't know. I may or may not watch Oprah. And Oprah has some guy, Dr. Oz, right? Dr. Oz. And he's on the show. He's like a health guru. He's like a nutrition expert. He's a doctor, Dr. Oz. And he's talking to Oprah, and he's like, Oprah, you're never going to believe this. It turns out that apples are the new arsenic. Apples are the new poison. That we just did a study, and it shows that apples are associated with a higher level of heart attacks. We compared food consumption for 50 different fruits to heart health, and we found out that apples are associated with heart attacks. This is crazy. Time for us to ban apples. See you later, Applejack. Superficially, it actually sounds commendable, doesn't it? And it makes sense how someone could fall into this sort of pitfall. Like, if you're a researcher and you compare, you're like, hey, I got 50 different fruits I want to look at. I want to look at not just apples, but pineapples and kiwis and limes and all those other crazy things that are in the supermarket. I don't even know the names of half of them. Dragon fruit. It feels like you're doing your due diligence. You're creating more work for yourself because you want to be thorough. It feels like a good thing. But in reality, it's bad. That's what we're observing, right? This is like an important big picture observation for us to make as professional statisticians, is that doing 50 different tests, looking at the relationship between heart health and 50 different fruits is performing 50 different tests. And if we do all 50 tests at the 0.05 significance level, we're virtually guaranteed to make at least one type 1 error. And that's what's happening in our Dr. Oz example, right? You test enough fruits, one of them will be falsely significant. One of them will show up as being like, oh, look at that. Apples are now deadly. Probably not really. It's just, right, there's always a 5% chance of a fluke sample. We just happen to sample, right, in our apple group, we just happen to sample a bunch of people that just, bad luck, they had bad hearts. It had nothing to do with the apples. It was just a fluke sample. And I guess it's cool. We're on the Oprah show, but we're also kind of spreading nonsense, right? And I think if anything, right, these recent years have really shown us that now more than ever, we really, really, really need to commit ourselves, right, to the highest principles when it comes to, right, communicating truth. And again, right, I hope we can see it's often not malicious. It's often well-meaning, but it is a misapplication of statistics. So one thing that non-statisticians like to do is lots of tests, but the reality is you shouldn't be doing that because you're going to find a false significance, or you're going to apply some sort of adjustment. You're going to have to do this Bonferroni adjustment, but this Bonferroni adjustment's overkill. So if you're doing 50 tests, now instead of comparing to 0.05, you're comparing to 0.05 divided by 50, and now you're like over penalizing yourself. It's kind of going in the other direction. There might actually be a meaningful relationship, but you've created such a difficult hurdle. The p-value has to be so crazily small to register as significant that you're just going to miss out on something. And so what's the solution? The solution is to have small targeted hypotheses. You don't just do like a shotgun scatter shot. Say, I'm going to test 100 things and see what happens, right? Realistically, you should go into any research problem, any research design as strategically and as targeted as possible, making as few tests as possible to minimize this very big problem. Whew, that was a lot of words for one PowerPoint slide. Tired myself out. Let's make this slide a little shorter. Another adjustment is the Tukey-Kramer. The Tukey-Kramer method guarantees that your overall type 1 error rate will be exactly 0.05, assuming you're doing all possible pairwise tests for a one-way ANOVA. That is, right, the Bonferroni is great because it's so general. Tukey-Kramer is the opposite of that. It's hyper specific, it's hyper specialized. But it's hyper specialized for the exact example we're talking about right now. So anytime we're doing this one-way ANOVA, we should be using the Tukey-Kramer adjustment. And in other situations where we're doing lots of tests, perhaps consider Bonferroni or Bonferroni-Holmes. We can compare means and make these corrections using the means statement in Proc GLM. We can use the Bone option to do a Bonferroni correction. We can use the Tukey option to do a Tukey correction. We said for the one-way ANOVA, we should be doing the Tukey correction. Right, so there it is. There's a mean statement. You put your categorical variable, in this case, slash Tukey. And there are our means, right? So we see the mean for treatment 1, the placebo is 7.5. The means are now ordered from highest to smallest. So the worst treatment was the placebo. The best treatment was treatment 3. Now look over to the left. You'll see something called the Tukey grouping. There's a bunch of A's. The treatments that all are in the A groups are not different from one another. That is, if you compared them after adjusting, they would not be significantly different from one another. So treatments 1, 5, 4, and 2, they all fall into the A grouping. Notice 3 does not fall into the A grouping. It's just 1, 5, 4, and 2. So 1, 5, 4, and 2 are sort of statistically indistinguishable from one another. We also have the B grouping. That's 5, 4, 2, and 3. So treatments 5, 4, 2, and 3 are indistinguishable from one another. All right? So the only two treatments that would test as significantly different, right? Because you're only statistically significant if you're in two different, if you're not in the same group, is treatments 1 and 3, because treatment 1 is only in group A and treatment 3 is only in group B. So after adjustment, right, the only treatments that are different, significantly different, are 1 and 3. Does that make sense? It takes a little bit of practice to get used to this kind of grouping method. If none of them were different, what we would see is just all A's. We would see no B's. If there was no significant difference, then it would just be A all the way down to treatment 3. And if they were all significantly different from one another, what we would see is an A, B, C, D, and E. Does that make sense, hopefully? Yeah, so here we are. Treatments 1, 5, 4, and 2, those are group A. They're not significantly different. Treatments 5, 4, 2, and 3, they're in group B. They're not significantly different, which implies that the only groups that are different after making our Tukey adjustment is treatments 1 and 3. All right. So a little bit of homework. Read the following article. There's the link for it. It's relatively short, pretty easily accessible article. Talks about this multiple comparison problem and kind of why it's a problem and sort of how widespread of a problem it is. And so there will likely be a question on this in your final exam. So make sure you read it. You don't have to turn anything in. Just, you don't have to memorize the article. The question that'll be on your final exam will be general enough that if you've read the article, you should be able to answer the question. All right. All right. See you for the final. Be brave. Stay wild.